Good afternoon, students. Welcome to the lecture 11 revision class of design of machine members 1. So in this session, we'll discuss about the concept of design of welded joints. So we are having the concept of design of welded joints in this lecture 11 as a revision class. Okay. So in the lecture 9 and lecture 10, we have discussed about design of riveted joints, their problems, their problems. In this lecture, we will see about the design of welded joint. So what is this joint? See here, you are having this plate, you are having this three square brackets, the square rods where you have welded in this manner, right? So this is the welded portion, how well it is welded. Okay, now a welded joint is a permanent joint. Okay, so the rivet joint is also a permanent joint, boiler joints, welded joints, brazier joints, soldering, these are all comes under the permanent joint list. Okay, a welded joint is a permanent joint which is obtained by the fusion of the edges. Fusion means melting of the metal and depositing on the same base metal, right? By the fusion of the edges of two welded parts to be joined together with or without application of pressure and the filler material. A welded joint is a permanent joint which is obtained by the fusion of the edges of the two parts, which is to be joined together by application of pressure or without application of the pressure. Then that is known as a welded joints by making use of a filler material. Okay, a filler material. Welding is extensively used in fabrication process. Fabrication is construction. Construction of any setup. Welding is extensively used in fabrication as an alternative method for casting or forging and as a replacement for bolted and riveted joints. It is also used as repair medium, example, to reunite. Reunite means again we are mating the components as at a crack. And for example, if you are welded two metal components, you are welded suppose two metal components. So at this point, whenever you got weld, at some point of period of time it has been welded, and later if you are seeing any crack on the welded portion, then what you will do? Again you will go for welding, that is reuniting the metal at a crack to build up a small part that has broken off, such as a grey tooth, or repair of a bond surface such as a bearing surface. So these are the examples where the crack is visible. The crack is obtained, that is a grey tooth or the bearing surface. Next, the welding is commonly used as a permanent joint process thanks to the great advancements in welding technology. It has secured a prominent place in manufacturing machine components. A welding joint has the following advantages. What are the following advantages? It is less expensive concept. Forming, forming a joint in difficult locations is possible through welding. Next, welding joints have smooth appearances. Due to the flexibility in the welding procedure, alteration and addition are possible. Next, since the added material is minimum, the joint is lighter weight. The joint is a lighter weight. Compared to the other types of joints, the welded joints have higher efficiency, that is less than 90, greater than 95% is achievable. Okay, greater than 95% is achievable. Due to the flexibility in the welding procedure, alterations can be possible. The advantages have made welding suitable for joining components in various machine structures. Okay, next, types of welded joints. What are the various types of welded joints? So if you see the various types of welded joints are already discussed in the production technology subject as well as in the machine drawing. So we are having more than 5 types, 4 to 5 types of welding joints. The first one is a lap joint or filler joint. Second one is a butt joint. So in the lap joint or a filler joint, single transverse joint, double transverse joint, parallel fillet joint. Okay, So single lap joint, single transverse or double transverse, parallel fillet joint. Okay, parallel fillet joint. See here the stresses are forced in this direction, right? Opposite direction, and opposite direction. Next, coming to the lap joint, you are having single transverse joint, double transverse joint, and parallel fillet joint. So the fillet joint, the fillet joint are shown in the figure. The transverse fillet joint has the disadvantage that the edge of the plate will not get weld, can buckle or warp out the shape. The butt joint, this is a square butt joint. This is a square butt joint. This is a single V-shaped butt joint. There is a single U-shaped butt joint. This is a single double U-shaped V butt joint. That is double U-shaped U butt joint. So these are the various types of joints that are used in the butt joint concept. You can see the butt joints may be a square type, single V type, right? Single V type, double U type, double V type, double U type. Right? If you see the rods or plates that are joined with a corner joint, the edge joint, and the T joint can be shown. See here, this is a plate 1 and this is a plate 2, or a pipe 1 or a pipe 2. So this is called as a corner joint. This is called as a corner joint. Next. So if you want to make a edge joint for any two small plates or steel pipes or metal, any metal pipes, this is nothing but an edge joint. Then it is a T joint. A T joint means where you are getting a joint at this one edge, other one is at the other side of the proportion. The main considerations involved in the selection of the welding type are the shape of the welded component, right? So they will see the shape of the welded component. Next, the thickness of the plates that can be welded. The thickness of the plates that can be welded. The direction of the forces applied. The direction of the forces applied. Next, the strength of transverse fillet welded joint. The strength of transverse fillet welded joint. So we'll see the type of this lap joint. We are seeing the various strengths. Okay, so see this figure. So you are having a plate 1, you are having a plate 2, right? This dotted portion ఏంటి? This plate 1 is under plate 2. ఇంకా plate 2 అనేది పైకి ఉంది, plate 1 అనేది కిందకు ఉంది. So see here, this is a plate 1, this is a plate 2. So ఈ డాట్ పోర్షన్ వచ్చేసి ఇది చూపిస్తుంది, రైట్? సో అంటే ఈ లైన్ ఇది అన్నమాట కింద కనిపిస్తుంది సైడ్లో. You can see everything, right? So in the top portion you can see this is nothing but transverse fillet weld. If you see on the top surface, you can see this S portion is a welding area. Okay, now if you see on the top side, so this side, this one, okay, so this is single, that is single. So you are having two type, 1 and 2 double transverse fillet joint. So depends upon the application, the pressure, the joint may be differ. That is a single type, and the other one is a double type. Next, if you see, in order to determine the strength of the fillet joint, please assume that the section of the fillet is a right triangle ABC. This right triangle ABC, the hypotenuse AC making equal angles with other sides AB and AC. Okay. The length of each side is shown as a leg or a size of the weld, and the perpendicular distance of the hypotenuse from the intersection of legs, that is AD, is known as the throat thickness. Okay. So see here. Now if you see here from the figure, let T is equal to throat thickness BD, this one. The welded area. This is the welded area. This is the B thick throat thickness, BD, that is thickness. Next, S is equal to leg or size of weld. There is S here. This S is equal to leg or size of the weld. Next, or thickness of the plate. We can say the thickness of the plate. L is equal to length of the weld. Total L is equal to length of the weld. Next, what shall we find that? Throat thickness. We find that throat thickness, which is there. T is equals to S into sin 45. There is 0.707 S. The minimum area A is equal to throat thickness into length of the weld. That is equal to T into L is equal to 0.707 S into L. Now, sigma T is allowable stress for the weld. Therefore, the pressure P, the tensile strength P is equal to the throat area into allowable shear stress. That is so if you see the throat area into allowable shear tensile stress, so this is the throat area into allowable stress. Therefore, the tensile strength for a joint for a double fillet means into 2 into 0.707 S into L into delta T. That is this one. Next, strength of a parallel fillet weld joint. It is the strength of the transverse fillet. Now, it is the strength of the parallel fillet process. So, see from the top view. See from the top view. పైకి చూడండి. The parallel fillet weld joint are designed for shear strength. Consider a double parallel fillet joint as shown in the figure. We have already discussed in the previous article that the minimum area of the weld of the throat area A is equals to S into L into 0.707. If tau is allowable shear stress for the weld metal, then the shear strength of the joint for a single parallel fillet weld P is equals to throat area into allowable shear stress, that is 0.707 S into L into tau. Therefore, for double shear, this one. See here the double parallel fillet weld. So finally choose that. This is plate 1, this is plate 2, this is also 2 welded pieces. And if you see that in that casing only, right, if you see any square or this parallel type of weld, okay. So here you have only at the two side. In this figure you are having the other side here also. That is the combination of transverse plus parallel fillet weld. Okay. Now if you see third one is the butt joint. In the butt joint, see here the thickness and the force is pulling in this direction and in this direction. But there are the bank is together. So therefore, when a force is applied in this direction, the force is applied in this direction. So whenever you are making for the double V joint, also nothing happens, right? So here you are having a single V joint and you are having a double V joint. Okay, here it is a T1, T2. Now in a single case V jet, the throat thickness of the weld is considered to be equal of the plate thickness T. Therefore, the strength of the joint is equals to T into L into delta T, where L is equal to length of the weld, that is the width of the plate. V is equal to butt joint under tension. H1 is equal to throat thickness at the top. H2 is equal to throat thickness at the bottom. Therefore, the tensile strength of the joint is equals to H1 plus H2 into L into delta T. Okay. Next. So this is for fillets, welds under torsion. So this is the calculation for fillet welds under torsion. Right. So the circular we will take now here the circular fillet weld. The figure shows the circle shaft connected by the plate by the fillet weld of the leg length T subjected to the torque and the shearing stress in the weld in the horizontal plane. Coinciding with the plate surface, coinciding with the plate surface, it is given by tau is equals to T into D by 2 divided by J. That is equals to J is equals to pi T D into D of D by 2 whole square. That is equals to tau is equals to 2T by pi D T cube. The maximum value for the shear stress occurs in the weld throat, the length of which is T by root 2 is equals to tau max is equals to T 2T root 2 divided by pi D T square. That is equal to 2.83 T by pi T T square. Next, load adjacent fillet welds. Load adjacent fillet welds. This shows a vertical plane connected by the horizontal plane. So it is simple nothing but a T plate. Now if you see the welded portion T, welded portion T, is a width, this is a axis, the direction, the direction. Okay, this is a chart. The T about the vertical axis of the joint. Okay. So capital L is equals to length. The general is a length. About the vertical axis, L is equals to length of the joint, T is equals to length of the weld. Now the effect of applied torque is to be produce shear stress. Now the horizontal coinciding the top surface is given by tau max is equals to 4.2 T by T into square. Next, fillet welds under bending moment. Now see the cross section, see the side view. So this is weld one, this is weld material, this is also second material. This is a just your flat object over a round piece. So how to get weld? So you have to weld on both all degrees of the object. Then only you can get this type of welded joint. Okay, that is equal to D is equal to R. Now the angular fillet joint M is equals to annular fillet weld subjected to the bending moment M. To determine the maximum bending stress induced in the joint, let us consider a small element in the weld that is at the theta angle. Therefore, area of the element R into d tau d theta into t, where t is equal to size of the weld. Normal force acting on the weld element dF is equal to R into d theta into t into tau t. Okay. Next, the normal stresses induced in the element sigma t max by 1 is equals to sigma t by 1 into r into sin theta. Sorry, r into sin theta, where sigma is equal to normal stress induced in the weld element, tau max is equal to maximum bending stress, tau t is equals to tau t max sin theta. Movement due to the force dF about the neutral plane is equals to dF into r into sin theta. That implies r tau theta to t into delta t r t I n theta. Therefore, r into d theta into t plus tau max into sin theta r theta. Right? Now, r into d theta into t into sigma t1 into r d sin theta. Therefore, r into d theta into t into tau t max sin theta r cos theta. So this can be written in this way. Now the total resisting moment offered by the weld is equals to r square t into tau t max into I. Therefore, m is equals to this one. Sigma t max is equals to m by r t to tau x. Next, considering the throat area, tau max is equals to m by d2 whole square into t into 2 root t into theta is equal to. Now, if you see the example problems, the figure shows the cylindrical rod of 50 mm diameter welded to the flat plate. So this is a flat plate. So on this flat plate, you are having a cylindrical object. You are having a okay. Now this is a now this is a plate. This is a cylindrical rod. The cylindrical fillet weld is loaded eccentrically with a force of 10 kN acting 20 mm. Then with the size weld is 20 mm. Determine the maximum normal stress in the weld. Now solution, let H is equal to thickness that is equal to T by root 2. From this design data book, introduce the two equal and opposite forces F1 minus S2 and parallel to the F. Therefore, passing to the center of the rod at the fixed end such that F1 is equals to F2 is equals to F. Okay, F1 is equals to F2 is equals to F. Effect of F1 is equal to F is not produced to transfer shear stress tau. Therefore, the area A is equals to pi dh, that is equal to pi into 50 into T by root 2. That implies 2221.8 mm square. Now the transverse shear stress, this can all the formulas you can see the design data. Tau is equals to F by A, that is equal to what is the initial one and the chinna, that is 10 into 1000 divided by 2218, right? 2221.8 is equals to 4.5 Newton square, right? Now F1 minus F2 is equals to F minus F. Therefore, M is equals to FL into FL, that is equal to F is equals to 10 into 1000 into 200, that is equal to 20 into 4 of 5. For circular fillet weld, Z is given by pi d square by 166. Therefore, F is equals to the value. Z is equals to this. Now the bending stresses. Bending stress sigma B is equal to M by Z. That is M also, Z also. We get the value. Now the maximum normal stress tau B sigma B is equals to root of tau square plus sigma B whole square, that is equals to this one. Next one. Figure 2.24a shows an eccentrically loaded weld joint determining the fillet weld size and allowable stress is 80.80 a. Okay. Now what is given? See here the figure itself gives the data. Amplitude with the weld from 50. Total is 400 plus 5. The force is 50 Newton. The width of the plate is 200. So when I transverse ichadu and also parallel and transverse. The given data F is equals to 50 kilonewton. This one 50 kilonewton. P is equals to 200 mm. This breadth is equals to 200 mm. L is equals to 150. F is equals to 80 MPa. Let T is the size of the weld. H is equal to throat thickness, that is equal to T by root 2. The distance from the center of gravity G. See here G. From the left edge of the plate, X is given by L square by 2L plus P. Therefore, L and the 150 square divided by 2 into 150 plus 400, sorry, 200. That is small e is equals to, right? Small e is equals to 400 plus 150 of x. Therefore, there is 505 mm. The polar momentum of inertia about the G, this formula. Design data book lo dorugutundi. So substituting these all values in this, you are getting finally Z value. Minimum radius, maximum radius of the weld GA, that's equal to R max is equals to root of AB square plus AC square, that is equal to 1000 square plus 1 square. So that is equal to 145 mm. This one. AB square plus AC square. AB square plus AC square. Okay. AC square. Right. On that figure we are getting 1.5. Therefore, cos theta is equals to GB by GA, that is equal to GB is equals to 105, GA is equals to 145, that is 0.74. Now the throat area of the weld A is equals to P plus 2 into L into G by that is equals to this value. Now referring with the 2.24B, this B portion, that is considered to equal and opposite forces, that is F1 minus F2 through G and parallel to F such that F1 is equals to F2 is equals to F. Therefore, F1 is equals to F. Therefore, primary shear stress tau 1 is equals to F by A. F1 in the A is equal to this one. We are getting this one. The effect F minus F2, this one, tau 2 is equals to Fe by Z into R max. That is equals to 105 by 0.6 by T. The resultant maximum shear stress tau max is equals to root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. That is equals to this one. That implies this one. T finally is equals to 14.5 mm. Next problem. A plate of 100 mm thick wide and the thickness is 10 mm is to be welded to another plate by the means of double parallel fillets. The plates are subjected to what static load of 80 kN. Find the length of the weld if the permissible shear stress in the weld does not exceed 55 MPa. Now what's the given data? Given width is equals to 100 mm, thickness is equal to 100 mm, P is equals to 80 kN, tau is equals to 55 MPa, that's equal to 55 Newton per mm square. See the given data. L is equal to length of the weld, this is the size of the weld, plate thickness is 10 mm is given. Now the maximum load that the plates can carry the double parallel fillet weld P is equals to this formula. Substituting all this one, you will get the L is equals to this one. L is equals to in mm's, that is 103 mm. Okay, so L is equal to 103. Adding 112.5 mm from the starting and topping of the weld run, we have L is equals to 115.5 mm. Okay, the stress concentration factor for welded joint for different types of welded joints. What's the stress concentration? Reinforced butt welds purchase 1.2, toe of transverse fillet welds purchase 1.5, 2.7, and 2. Understood? So if I wanted to find the length of the weld, so that's why the length of the weld is this one. So how you got this 12.5? 12.5 is from the weld run. Okay. Now next problem. Okay, this. Now see the next one. A plate of 75 mm, a plate of 75 mm thickness, wide, and 12.5 mm thickness, thick. So here is the plate width is 75 mm, and the thickness is converted to thickness is 12.5 is joined with the another plate by a single transverse weld and a double transverse fillet weld as shown in the figure. The maximum tensile and shear stresses are 70 MPa and 56 MPa respectively. Find the length of each parallel fillet weld. The joint is subjected to the both static and static loading. Then what is the given data? Width is equal to 75 mm, thickness is equal to 12.5, tau is equal to 70 MPa, tau is equal to 56. Okay, the effective length of the weld L1 for the transverse weld may be obtained by subtracting 12.5 mm from the width of the plate. Therefore, L is equal to 75 minus 12.5, that is 62.5. So why we have to subtract here? Because the L1 for the transferred weld may be obtained by subtracting this one, subtracting this one, that is 62.5. Together this one and this one 12.5 na తగ్గించాలి. Now the length of each parallel fillet weld, the length of each parallel fillet weld for the static loading, that L is for L length is L2 is equals to length of parallel fillet. The maximum load which the plate can carry is E is equals to area into stress, that is area into stress. Okay, 70. This one stress. Therefore, this is a P. Now the load carried by the single transverse weld P1 is equals to 0.707 into S into L1 into sigma T, that is this one. That is equals to 3838664 Newton. Now the load carried by the point P, this one is equals to P1 plus P2, that is P1 also plus P2 also. Therefore, L2 is equals to 27.2 mm. Adding 12.5 mm for the starting and stopping of the weld run, we have L2 is equals to 27.2 plus 12.5, that is 40 mm. Now the length of each parallel fillet for the fatigue loading, which is for the static loading, here it is for fatigue loading. From the table which is in the design data book, permissible tensile stress is equal to this one, is equal to 1.5, that is equal to 46.7, and the permissible shear stress tau is equals to 20.74. Load carried by the single transverse weld P1 is equals to so S into L1 into sigma T, that's equal to this one. For the load carried by the double parallel fillet weld, that is equal to this one. Load carried by the joint, therefore pressure is equals to load is equals to P1 plus P2, that's equal to P1 plus P2, that's equal to L2 is equal to 1.8 mm. Adding 12.5 mm for starting and stopping of the weld, therefore 1.8 plus 12.5, that is 121 mm. Okay, next, design of bolt joints. Here we are having only the design concept of the bolt joint. Okay, the threaded fasteners, bolts, screws, studs are the common types of threaded fasteners. Threaded and enti, we are having a thread on the surface of the any rod. Then we are calling them as a screw or a bolt. Bolt might get lost in it, so the bolt is like this. Okay, so the bolt flat ga untundi, screw anedi ela untundi, screw is having a taper portion, but here also we are having a threads. Okay, here also we are having threads, here also we are having a threads. They are used for both permanent as well as removable joints. Then what are the bolts here? The bolts are basically threaded fasteners, normally used with the nut. Together, normally used with nuts to assemble. Then what are the screws here? They engage either with a preformed or self-made internal threads. Next one is stud. They are externally threaded headless fasteners. Okay, one end usually meets a tapped component and other end with a standard nut. There are different forms of bolt and screw heads for a different usage. These include both the heads of the square, hexagonal or I shape and the screw heads of hexagonal filters. Okay, now to see the different types of this bolts, screws. See here is a flat blister head. Children, flat blister head. We can keep a screwdriver here and we can rotate. Oval shaped blister head. Oval shaped blister head. Next is a flat or countersink head. This is a round or button head. Now, design of the bolted joints. What are the first thing? Stresses in the screw fasteners. It is necessary to determine the stresses in the screw fasteners due to the both static and dynamic loading. In order to design the static loading, both initial tightening and the hexagonal loading need to be known. Then we'll find the initial tightening of the load. When a nut is tightened over a screw, following stresses are used. First one is tensile stresses due to the stretching of the bolt, torsional shear stress due to the functional resistance at the threads, shear stress across the threads, compressive or crushing stress on the threads, bending stresses under the bolt head. So here under the initial tightening, we are having the tensile stress. Tensile stresses. So for this tensile stresses, sigma is equals to 284D divided by 5/4 square bolts of smaller diameter. Second one is torsional shear stress. The torsional shear stress tau is equals to 16T by pi dq. Okay, T is a torque, Tc is a core diameter, and we may relate torque T to the tightening of load P1 in a power screw configuration, and taking collar friction into the account, we may write T is equals to P1 into dm by 2 into 1 plus mu dm secant alpha by pi dm plus ul into secant alpha plus P1 UC dcm by 2. Now third point is shear stress across the threads. Tau is equals to 3p by pi dcbn. dc is equal to core diameter, b is equal to base width of the thread, and n is equal to number of threads sharing the load. Now the fourth one is crushing stress on the threads. This is given by crushing stress sigma c is equals to p by 5 by 4 p outer minus d crushing. Next one is a bending stress. Next one is a bending stress. So when you get a question design of weld joints, design of the bolt joints, so just initial load in the graph, first thing is to determine the tensile stress, to determine the torsional shear stress, to determine the shear stress across the threads. Next, to determine the crushing stress on the threads, to determine the bending stresses. So like this you have to derive. So with this we have completed the welded joints also. Okay, so definitely in this lecture 9, lecture 10, lecture 11 definitely you will get one question in the main exam. So practice the questions in well advance and prepare for the exam. Okay, so if you have any doubts, just we will discuss. Okay, design of the bolt joints. So these are the problems related to the welded joints. Okay, practice these problems, so definitely you will get some problems. Only if you are aware of your design data book, then automatically you can write something so that you can pass the MM1 very easily. Okay, so these are the concepts what we have studied in this lecture 11. Okay, na? Right? So theory questions, types of weld joints gaani, and the figures of this butt joint gaani. Okay, derivation of this transverse fillet welded joint gaani, parallel fillet welded joints gaani, you will get. Okay, next the problems you have to practice well. So with this we'll stop the class. So we will see in the lecture unit 2 and unit 1. Okay. So thanks for watching the video. Have a nice day.